Welcome to This Explainer. Today, we're going to strip away the illusion of simplicity and reveal the incredibly elegant mathematical language required to teach machines how to move. I mean, if you've ever watched a robotic arm seamlessly assemble a car, or maybe seen a mechanical hand gently grasp a fragile object, you might actually think the underlying mechanics are as natural as our own. But as we're about to see, giving a machine the gift of motion is absolutely anything but simple. Think about this for a second. Picking up a glass of water, it feels completely effortless to us. We aren't calculating angles, we're not computing distances, we just reach out and grab it. But for a robot, that exact same action requires a massive, complex framework of rules, coordinates, and matrices. So how do we translate the effortless intuition of human movement into the rigid, uncompromising language of mathematics? You know, our fascination with human-like machines actually stems right from storytelling. The very word robot comes from Carol Capek's 1921 science fiction play, RUR. We have literally always dreamed of machines that mirror our own image, complete with intelligence and personality. But the reality of engineering these machines is far more grounded. It's built not on sci-fi magic, but on rigorous mechanics and linear algebra. So let's kick things off with Section 1, Sci-Fi to Factory Floor, and trace how we got here. When you look at this chronological evolution, it's wild how fast robotics jumped from fiction to reality. Right after World War II, engineers were already developing teleoperators to handle radioactive materials safely. But the real game changer happened in 1954 when George Devol patented the first programmed articulated transfer device. Fast forward just a few years to 1961, and a company called Unimation installs its very first programmable robot at a GM plant. This was a total revolution because suddenly the machine could be retooled and reprogrammed for entirely different tasks without having to rebuild the whole thing from scratch. Now take a look at the Unimation Puma robot from 1978. It used what's called an open kinematic chain, which is essentially a cantilevered beam structure with multiple degrees of freedom. This was a brilliant design choice because it gave the robot a huge workspace relative to its actual size. But there was a major catch. Controlling the absolute endpoint of a cantilevered arm is incredibly difficult. Any tiny microscopic error at the base gets drastically amplified by the time you reach the end of the arm. It made really fine, delicate control pretty clumsy. Which brings us to Section 2, the quest for dexterity, and how engineers moved beyond those simple grippers. To solve that clumsiness, engineers had this massive biological aha moment, perfectly captured by neurophysiology. If you look at the brain's homunculus map, that's the map connecting body parts to the brain areas controlling them, you find something totally astonishing. Up to 40% of our entire motor cortex is dedicated exclusively to the intricate movements of our hands. We basically use our arms just to transport our hands through space, but our fingers do the truly intricate work. Engineers quickly realized that robots needed to operate the exact same way. And this brilliantly highlights exactly why a simple robotic pincer just fails at complex tasks. If a robot only has a basic claw, any tiny adjustment means firing up the massive, slow, energy-heavy motors at the very base of the arm. It's incredibly inefficient. On the flip side, multi-fingered hands offer lightning-fast, highly precise force control. They can instantly reconfigure themselves for different tasks, which drastically reduces the need to constantly swap out the robot's tools. So here we see that mechanical leap to anthropomorphic engineering in action. You've got the Salisbury hand, which is a three-finger design where every joint is driven by electric motors pulling a network of cables. Then you compare that to the incredibly complex Utah/MIT hand. That one uses four fingers and is driven by pneumatic pistons instead of electric motors. The goal here wasn't just to hold things securely. These hands were designed to actively manipulate objects right within their grasp, exactly like we do. All right, let's step into the math. Section 3, defining rigid body motion and the rules that make this all work. At its core, before we can even begin to calculate a robot's trajectory, we have to define what a rigid body actually is. We treat a robotic link as a perfectly undistortable object. This means that if you pick literally any 2 points on that body, the exact distance between those 2 points never, ever changes, regardless of how the object translates or rotates in space. Mapping an object from its starting position to its final position under these rules is what we call a rigid body transformation. Mathematically, we can basically boil this down to a two-step checklist. First, exactly as we just said, the length between any 2 points has to be rigidly preserved. But that alone isn't quite enough. See, a math equation could technically preserve length by reflecting an object into a perfect mirror image of itself. Since physical robots cannot magically turn inside out in the real world, we add a second rule. The cross product between vectors must be preserved. That guarantees the object maintains its correct physical orientation. So how do we actually track all of this? Well, it's kind of like tracking a character's position in a 3D video game. We attach a right-handed coordinate frame directly to the body itself. We then track the movement of this specific body frame relative to a completely stationary inertial frame, which just represents the fixed world around it. By knowing exactly how that single coordinate frame moves and rotates, boom, we immediately know the precise location of every single particle on that entire robotic arm.
Now let's zoom in even closer. Section 4, the rules of rotation and matrix mathematics.
To represent these rotations, we use 3x3 matrices that belong to a very special mathematical group called SO3. The absolutely crucial point here is that by strictly following the 4 axioms of a group, closure, identity, inverse, and associativity, engineers can flawlessly multiply sequence after sequence of rotation matrices together. This is what lets them mathematically track a robotic body as it continuously twists, turns, and updates its orientation through 3-dimensional space. Now, remember just a minute ago when we talked about preventing our robot from magically turning inside out? This is exactly where the special in the special orthogonal group, or SO3, comes into play. By mathematically demanding that the determinant of our rotation matrix equals strictly +1, not plus or minus 1, just +1, we lock the robot's coordinates firmly into the constraints of physical reality. It completely eliminates the possibility of those impossible internal reflections. So, we've successfully cracked it. We've stripped away the illusion of simplicity, traced the history from science fiction to the factory floor, and built the elegant, strict mathematical language required to rotate a robotic joint in physical space. But that leaves us with a really fascinating challenge. Now that we have the math to perfectly move a single joint, how do we actually plan its dynamic, coordinated path through a totally unpredictable world? How does it avoid obstacles and actually interact with objects? Well, that is a complex puzzle for another day. Thanks for joining me on this explainer, and remember to always keep questioning the simple things.